In an experiment to calculate the average force a snooker cue applies to a ball, a special force sensor is attached to the snooker ball, and the data of the size of the force over the time of contact is shown below. So this graph is telling us a story of how the force varies over a given time. Check the units of the axis. Force will be measured in newtons, and time is measured in milliseconds. Very important to know the units of the graph. So that's a force time graph. Now what can we tell from a force time graph? Well, first thing we can tell is how the force changes over the given time of contact. But the other things we can find from a force time graph are, by working out the area of the graph, we can find the change in momentum and the impulse. So the area of that graph, the physical area of the graph underneath the graph, is going to give us the impulse and the change in momentum. So what's going to be the area of that graph then? The area of the graph is going to be 1/2 times 10 times 10 to the minus 3. Remember, it's milliseconds. And you've got to multiply that by the height of the graph, which is going to be, at its peak, 9. We get an answer of 0.045 numerically. Now, what we can do now is put down the change in momentum, delta P, and the impulse, Ft. And both of them will be the same. 0.045 kilogram meters per second for the change of momentum of the ball, and the impulse given to the ball will be exactly the same numerically, 0.045 newton seconds. When you have an impulse, you have a change in momentum. When you have a change in momentum, you have an impulse. Both go hand in hand. Now, a common question after this is to find the speed of the snooker ball immediately after it's been struck. Or in other words, find the speed of the ball immediately after its change of momentum has occurred. So what we do in this case is the following. We just simply do the wee equation work like this. The change of momentum, delta P, is going to equal to mv minus mu, where mv is going to be the final momentum and mu is going to be the momentum before. But we do know that the initial velocity of the snooker ball is going to be 0, so we can drop the mu out right away, and we can see that delta P, the change in momentum, is equal to mv. M being the mass of the snooker ball, v being its speed or its velocity afterwards. Rearrange, we get the v equal to change in momentum divided by mass, 0.045 divided by 0.17 kilograms, and we get the speed of the snooker ball immediately after it's been given the impulse. V equals 0.3 meters per second.